Welcome to Build with Nods. In today's live coding video, I'm going to walk us through Tokio tracing and OpenTelemetry and how to use it in Rust applications. One of the coolest things about asynchronous Rust is the Tokio runtime, and it has fantastic support for tracing and instrumentation, and it actually connects up very nicely with OpenTelemetry, which can lead to some really cool observability features in any sort of serious applications that you might be writing. So in today's video, the general structure is going to be we're going to create a just a empty project and then add some tracing to it to see what tracing looks like, and then from that work up to looking at instrumentation and essentially how that works, the notion of spans in asynchronous code, and how that differs from logs. And then I'll show you some real examples in this tcp-api-server crate that I've been working on, which actually will showcase a lot of the more advanced features with adding layers to tracing, basically tracing subscribers and also connecting it up to OpenTelemetry and Jaeger, so we can actually visualize some of the traces. So with that, let's actually get started. The first part, what we're going to do is very quickly create a simple program so we can just walk through tracing and just kind of like give an overview of what it is. So let's do this. We're going to build a new crate called tracing OTel. Where did it go? Oh, that was interesting. Oh, VS Code issues. What? Okay. Let me see. That is so strange. VS Code actually crashed, and I had to restart it. Okay, with that restart out of the way, hopefully there won't be more restarts this way. So I just created a new binary crate called tracing OpenTelemetry or OTel. And then what we'll do is, since we're going to be using tracing, let's add some dependencies. So I'm going to add niet for error reporting. I'm going to add Tokio, and I am going to add tracing and tracing subscriber. So let's see what our cargo toml looks like at the end of the day. Let's see. Oops. There's our cargo toml. And here we have niet for error reporting, Tokio for our async runtime, tracing, which is also Tokio tracing, and tracing subscriber, which is the we're going to be using all of these. So let's see. The first program we have is a simple main function. So let's make it an async main function. And then what we can do here is that now that we've done this, let's run it, see if it works. Let's see. Ah, okay, hello world. Okay, perfect. So cargo run -q. It works. Okay, cool. So now let us make another function. So let's say we'll say async print message, and here we will just do this. This is all made up. I mean, I just wanted to essentially trace something or log something, and I'll explain the difference between traces and logs in just a minute, and spans and instrumentation and everything. So in order to do this, we have, there we go, there's our dependencies. So we need to make something called a subscriber. So there's two aspects to tracing. One is generating the events, such as calling the log macro, the debug macro, error macro, and so forth. That's generating the events. And then the other side is to actually do something or subscribe to these events so that we can format it and then display it to, let's say, standard out or a file, or maybe even send it to an OpenTelemetry collector and then visualize it in something like Jaeger. So we're gonna see basically all of the above, but let's start with the baby steps. So let's say the first thing we want to do is we're going to do tracing subscriber. And there's a create tracing subscriber FMT, so it's a formatted subscriber. And then at the most basic level, we can do something like that. Oops, where did Copilot was right. So we can say let subscriber is that. And then what this will do is that it'll create a subscriber, which is a formatting subscriber, meaning that it'll take the events and then format it, and then with the intention of displaying it to standard out in this case. But then to kind of add to this, we can add more layers, which we'll see later on in this video. So this is just the most basic sort of getting started. So here we're just going to pick mostly defaults. And then once that's done, what we do is we say the tracing subscribe. Oops, what the heck? What is going on with, there we go. Subscriber, and then we want to set the global default, and here we say the subscriber. And let's see. Oops, it's not init, it's actually finish. We can do this in one step by saying .init, but this, actually we can do like this, and that essentially does the same as, there's too many ways to use this library, but for now let's just stick with this. Let's see, so let's return a MEAT result, and that should, this is for MEAT. So that basically takes some different kinds of errors and then wraps them into a diagnostics report. So, and I'll do a separate video on MEAT later, so I will not spend too much time talking about MEAT in this video. And I'm planning to do another video on async Rust as well, which should be good. Okay, so now we have a subscriber. Let's just fill it out, subscriber. So here we have a subscriber, and we've configured it, set it as the global default formatting subscriber. So now if we run it, nothing happens because we've set up the subscriber, but we're not generating any log messages. So let's generate a log message. We say tracing info, and instead of hello world, let's just say log message 1. So let's see what happens. Check it out. So there's a timestamp. There's info, the log level, and then something called tracing underscore OTel and log message 1. So that's the module. Actually, for this, it's automatically generated, and then log message 1. So that's cool. Let's see if we can change some of those formatting a little bit. So here we can, there's a whole bunch of things you can do. Like you can change how these logs are displayed. This is called compact format. One I like is without timestamp, which is kind of, I feel it keeps the output a little bit cleaner. So there, it just dropped the time altogether. And then there's also something called pre, which is really nice. So we can do that. So it basically adds a lot of like character journal line feeds in between multiple log messages. So let's see, we can say tracing debug, and then we can say log message 2, and then here we can see what that looks like. So there's log message 1, then it displays hello world, and then there's log message 2. So that's actually the tracing crate in action. And so we're modifying some let's say configuration options for the subscriber. So you can see here there's all different kinds. There's like with timer, with ANSI, so you can do colorful output, with target, with or without line numbers, and so on. And there's another one called with writer, which we're going to look at in later on in the video. This is where you can essentially adapt any output device to be able to display whatever's coming out of this formatted subscriber. And we'll be able to add layers and a whole host of other things, and then even connect this to an OpenTelemetry collector. So this will become an emitter. So here we have we're successfully generating log messages. And so now the question becomes, okay, that's great. This is all in the getting started guide. This is wonderful. So there's something called a span. So like, what's the difference between a span and an event? So one of the reasons for Tokio tracing is that asynchronous code in Rust doesn't run sequentially, hence asynchronous, and especially when it's multi-threaded. So then we can have essentially a task that's awaiting. In other words, it's parked or paused, and then when it resumes, it can potentially resume on a different thread. And these are because Tokio manages its own worker threads. We don't know which thread it's gonna be run on. There's ways to actually constrain tasks to run on a single thread, but I will cover that in the next video on async Rust. But for now, let's just assume that we don't know which thread a task is going to be running on. So in that case, logs are generated as a singular or atomic event. So when a log output happens, it's got a timestamp and it's got some message. There really isn't a way to stitch a bunch of these log events together so that we understand when a particular let's say task had started and ended, how many events occurred in the middle. And so that's what spans are. They essentially decorate many different log messages with information about temporality and causality. So we'll see an example of what that means in in this video. But essentially, it's a way to understand how there's you can think of it as a life cycle of a function. And over its lifetime from beginning to end, it might call other functions. It might do so asynchronously, so it's being paused, resumed, paused, resumed, paused, resumed, and then this is happening over a multitude of threads. And so to make sense of all of this is why tracing was created. And so in order to enable that, we have to not just generate logs. These are those singular events in time, as you saw when we run it, but it doesn't really tell you the story of what was happening before or after or in the middle. So in order to do that, we have to do this thing called, we have to instrument our code. And this easiest way to do that is we can annotate our function with this attribute macro. And what this does is that under the hood, it actually generates, let's do this. So tracing, and by the way, if you trace something, so let's break this out a little bit further and say this is async, and we'll do prepare message which returns string. This is all made up, so we're just gonna kind of unnecessarily making this. So we'll do this hello world, and we'll do prepare message await, and then here we can just say toString. So now let's instrument this thing. So instrumentation, what it does is that it'll unwrap this code. You can read all about it here. It unwraps the code. Actually, I have a really good thing here. I asked Bard earlier, like, what is the difference between emitting like these logs and instrumentation? So this is actually a really good answer. Tokio tracing provides a way to collect structured and event-based diagnostic information, which is great. So we can do tracing info, tracing debug, and then these are the things that emit output to logs. The instrument macro, on the other hand, creates spans, and a span can be entered and a span can be exited, and a span can have a parent span, and a span can contain other spans. So in order, we could actually make these spans manually. That is a thing. So we can actually look at the, let's see, docs, rs, tracing. So we can create spans manually. So you can, a span has an ID, you can enter a span, you can exit a span. There's all kinds of things that you can do. And the idea is that when a span is created and entered, then all the functions that are called are part of that span. And so as log messages are emitted, they can be used to, essentially context can be provided for those log messages that come from the span. And so spans can have parent-child relationships. And you basically open a span, enter a span, and then you close a span, and then you drop it. But this is a little bit esoteric right now, but we'll make it concrete in a minute. And so the difference between instrument and the log, like info, debug, the log emitting, is that instrumentation doesn't actually emit anything. Instrumentation provides context and spans, which are then included when you emit logs with info, debug, and so on. So, and I'll put links to all of these in the video. So let's run this and see what happens. So nothing happened. It pretty much did exactly what we saw earlier, and this tracing instrument, even though prepare message is instrumented, it didn't actually reflect in the output. And the reason for that is that in order for us to see it in the output, we have to actually generate this tracing info, and then we can actually let's do debug because the other ones are info. So we can do debug. We can do let's see, info can do warning, and here we can do debug, and we can also do trace. So this is just made up for and there we go. So and this is just from my Kotlin days. I still use it. Okay, so let's run this and see what happens. Look at that. So we did info, which is log message 1, and then check it out. Log message 1 is right there. Then we call prepare message, and then look at this. It goes tracing debug. We have preparing message and message prepared. So here, actually, if we take out the instrument, let's see what the output looks like. It looks similar, and that's because we aren't really doing anything very interesting so far. So let's put this back. So where we can make instrumentation more interesting is we can do things like this. We can tell the attribute macro to tag or attach context to the log messages that are being generated as part of the span. So this is a particular span. This span says keep track of whatever it is that you return from this function. So when we run that, it looks like this. It goes tracing this one. It goes return hello world, and this it actually generated by itself because I put this ret in there. So this is really cool. Like once you start tagging your functions, or putting this attribute macro on your functions, all of a sudden they inherit superpowers. So essentially, another cool thing you can do is, let's say we change our function so that let's instrument this, and let's receive an argument. So we're going to say we take an argument as a message, and we'll say, okay, this is foo. And then when we prepare the message, actually, let's do this one step at a time. So here, if I just, without doing anything, if I just now run this function, run this program, you will see something interesting. It goes, the argument foo is now threaded through all of the log messages. So if we start at the top, it goes, the first one is, let's see, it goes, print message, and it goes log message 1. But because log message 1, this info log output is emitted inside of the span, and the span automatically picks up any arguments that are passed into it, you will see that all the subsequent calls are annotated with that argument. This is really cool. So we didn't have to do anything to make this happen. All of this is happening. Like I didn't add anything to the info or the warn or the debug, and it automatically gets annotated with contextual information from the span inside of which it's running, including return values. So this is one of the coolest things with instrumentation and logging. So Here, if let's say we don't want to see arg, we can just say skip, and then you can say skip all. And then what this means is that it will no longer display. You'll see that the arg is missing. It's not being displayed in the output anymore. You can also there's a whole host of other things that that you can do here. Like there's like this fields thing where you can do stuff like that. This is totally redundant because I mean by default it would this is return anything, so it's not going to really produce anything in the output. But these are just some of the things that you can pass. So return is unit because it doesn't return anything. And then you'll see that arg colon foo is now threaded through just like it was before. So and there's like these are called sigils, and you can do like this. Question is for debug, and percentages for display. So depending on what you need, you can change those sigils in the attribute macro. So this is pretty powerful stuff. And then you can even create fields which don't have values yet. So you can say something like client ID, and there is no such thing as client ID. And then you can say something like, I think a span. Yeah, you can do something like this where you can say for the current span, go ahead and set the value of this client ID to this number. So let's see what happens here. So again, these are annotating things. So let's see. If we run it, what do we see? We see client ID. So basically, it's threading it through. Like as soon as it becomes available, it's almost like a tree. There's like a and when we look at Jaeger, it will become very apparent how this is a tree. And so essentially, this client ID gets passed down to subsequent to basically other functions in this the call hierarchy, if you want to think of it this way. Because print message ends up calling prepare message, so because I annotated this prepare message span with this client ID, it gets passed down to prepare message. So this is actually pretty awesome. So arg foo, which came down from up in print message, and the client ID, which was generated in print message, also ends up getting sent down to prepare message. So check that out. And there's the return, and there's all the things that are make up the context of the span. So this essentially this is all the information that is missing from log messages, because in a log message it doesn't track the beginning and the end of, let's say, a journey. And so a journey is like essentially some function call which ends up resulting in many other function calls, and these functions can be asynchronous, and they're not, and they're because they're not synchronous, they're being paused, resumed, paused, resumed, paused, resumed, and then all of this is happening over multiple threads, and this essentially instrumentation makes sure that we can all make sense of it after this is running at runtime. And to visualize it, this log output to standard out isn't that helpful, but what we'll do with the next part of the video is when we get into OpenTelemetry is we can see how some of the stuff, what it looks like when we look at OpenTelemetry in Jaeger. So with that, one of the projects I am going to use to actually demonstrate this is this tcp-api-server, which is in this repo, and I'll link to this in the video as well. It's in the Rust Scratch repo. Inside of that, there's a folder. This is a mono repo which has a bunch of other crates in it. tcp-api-server is one of those crates. And let me walk you through real quick what this project is, because this is going to be the quote-unquote real-world project that I'll be using to demonstrate like real usage of instrumentation, of spans, of tracing, attaching multiple layers. So because we want to be able to emit logs, not just to standard out like we saw here, which is okay, but I mean it's pretty basic. We might want to emit logs to files, to standard out. We might also want to emit them to asynchronous standard out, because I built a crate called Rebel Terminal Async, which provides a asynchronous readline and asynchronous standard out or standard error, basically standard in, standard out, standard error, but all asynced. And so we can actually use that this async standard out or async standard error as a way to emit our log output, not just standard out and standard error, which are sync. And then so this notion of layers for subscribers comes into play. We actually, in this example, are just using a single layer, which by default is formatting the log messages and then dumping them to standard out. But we'll extend this so that instead of just having a subscriber with a single layer, we can have a subscriber with many, many, many layers. And we can actually configure those layers at runtime. And then finally, we'll look at how we can add yet another layer, an OTel layer, OpenTelemetry layer, which will send these log messages not to standard out, but to an OpenTelemetry collector, which will run using Docker. And then we'll see what the output of that looks like in something called Jaeger. So with that, let me walk you very quickly through what this particular project does to give a sense of like, okay, what are all the pieces that need to that come into play. So our basic example was kind of got the notion of instrument and how that works with info and warn and all the log emitting. But what it doesn't show is any kind of complex configuration. So this TCP-API server thing is a crate, and what it does is it when you run it, you can run it as a server and you can run it as a client. When you run it as a server, it provides a simple API which allows you to perform CRUD operations on a persistent key value store. And all the communication between the client and the server happens using this custom protocol, which is defined in this crate. And also the client side of this is using Rebel Terminal Async. So let me just walk you through what it looks like, and then we'll refer to this architecture diagram real quick. Like this is, and I'll do a separate video on tcp-api-server as well, and an article on developer life. So for now, let us look at this. So this is, let's run the server and see what it does. Also, if you noticed, there's a colorized output for from clap. So I'm going to do a separate video on clap as well and discuss how to do colorized output like this. Cargo itself uses colorized output, so this is a thing that it makes it look really nice. So here, let me run just general help on this. So essentially it's a TCP-API server is the binary, and you can pass some commands to it. You can say start the server or start the client. And the thing that we're going to be looking at here is configure tracing. So when you configure tracing, you can say, okay, don't trace anything, or trace to standard out like we did in this example, or trace to file, which is actually emit all the log output into a log file, or log files, one for the client, one for the server, or to standard out and to file. So this is both for standard out and file. And the default is standard out and file. And later on, we'll look at this OTel collector endpoint for emitting these events to the OpenTelemetry collector, or exporting them to the OpenTelemetry collector. So for now, let us run the server without any options. Just say, oops, TCP-api-server, or just say server. Okay, and it goes. Actually, let me clear the screen and do this. Okay. So it goes main event loop, starting server, and it goes listening for connections. So let us do this. We can say client. So here, if we say debug, this means that we're telling the binary, hey, I want to show up to debug messages. So that means inclusive of debug. That means debug, info, warn, but not trace. Essentially, just omitting trace. Or we can just say info. The default is info. If you do this, the default is info. Yeah. So you can override the log level, which is nice. And I'll walk you through the code for this in a minute to see how to configure all the different layers because setting a filter on the level is one of the layers, or one of the ways in which we configure a layer. So let us just run this with the defaults, and this is kind of like what it looks like. It goes connected to server, and this one goes, oh look, I have a connection from the server. See this italicized thing? That these are those the instrumentation macros with certain fields that it's tracking. So it gives a nice connection between, because you can have multiple clients. So let's say we run here. Where did it go? Let's see. We can do, actually, let us run in this terminal. How do I do this? Let's do this. So here we're going to run another client. So I have one client running in this window, another client running in that window, and then the server's here. And as you can see, the server is now connected to two clients, which is cool. So because that one server process can connect to any number of clients, each client gets a client ID, and that just makes it easier for us to track these things in the logs. So we'll see the value of this later on in the video. So here, let's look at this client. So it connected to the server. It gets an ID, and that's part of the protocol. So essentially, if we look at the protocol, there's this, oops, let me just cancel out of this. So there's basically, this protocol is a binary protocol, and it specifies all the messages that get sent from the client to the server, and all the messages that get sent from the server to the client. So all of this is described here. And essentially the client and the server parts of the code implement their respective parts of it. So the client, and I'll show this, the client application sends client message to the server, and the server application sends server messages to the client. So so when a client first connects to a server, it gets a unique ID, and this is a use of instrumentation just to kind of see that unique ID, and we'll see that in the logs later, and it'll be a way to stitch together all the interactions that are happening on a particular client session with a particular server session. So it's the same session that's on both ends. So here another command we can do size, for example. So that essentially just queries the server, because the server actually spawns a key value store. And so when I type size on the client, it asynchronously connects to the server, gets the response, and displays the message. So this is that Rebel terminal async. All of this is happening asynchronously, so none of this is blocking the main thread. And then, so when I say size on the client side, it sends it to the server side. And I'm kind of like walking through this, kind of using instrumentation as a way to tell the story. So here we can see there's the client, Duke Apple 808 right here, that sent the request, and then it said, what is your size? And then it sent, actually, this is where it got it. It goes, client ID is asking for the size, and then it goes, the server goes, I got the size, and I send it to the client. And the client goes, let's see, so when I typed size, the client says, hey, I'm sending a message called size to the server, and then it goes, the server responded with the server message, which says size of 3, and so I received the size, which is 3. So we can also do something like this, get all. And this essentially does a similar thing. The client goes, hey, get me, what are all the key value pairs on the server? The server goes, okay, let me go get the key value pairs, package it up, and send it back to the client, and the client then just displays it. So this is, and with tracing, you can see how we can see this happening, and this is just from the traces. This is really cool. And then once we see this in Jaeger, it'll be even cooler. So let me exit this, and then that quits from the client, and then I can quit the server. So essentially that's the what's actually happening in this TCP API server. And you've already seen the log output. So how did all that happen? Also, if we do this, let's do this. So let me actually open another terminal, and then let's see, I can say tail f client log, and then here we'll do tail f server log. There we go. So here, when I run the server, you can see that the server log is being updated. So not only are the log messages being displayed to standard out, but they're also being dumped to a file. When I run the client, not only are the log messages being displayed to standard out, but they're also being dumped into a file. So this is really cool. So we can have the same output happening on both sides, because we can disable, let's say, the client output. Like if we do help, we can just say, I only want to see the, let's say, trace output to file. And so now we won't see any noise in standard out, but we'll still see, as you can see here, all the messages are, all the client messages are being output to a log. So this is pretty cool. It works. So let's see. Let me just quit out of this because this is a lot of logs. Okay. So let's look at how this is actually configured in here. So essentially, there's some clap configuration that I've specified to be able to define or declare which like whether standard out file or standard out and file should be used to emit log output. And then this enable tracing is used by the main function. So when you run this tcp-api-server or client, so there's a server or the client, it runs this main function. And in this main function, if it's the client, if it's a server, as you can see, it displays this tcp-api-server logo. And if you say client, it displays tcp-api client. So you can at least keep track of which one is a server, which one is a client. And that happens here. But going deeper, there's another crate called Rebel Terminal Async that this project uses. And inside of Rebel Terminal Async, there is a way to configure tracing. And in order to configure tracing, you have to tell it like what your intention is. How would you like to trace things? And so so here's where you specify like what is the log level, the file format if you're using file output, and if you're emitting logs to standard out, this is where you can say to normal standard out, or you can output to this thing called the terminal async shared writer, which is basically an async standard out or an async standard error. It's what's used so that the output from asynchronous tasks in this console does not clobber the prompt, and the prompt doesn't clobber. That's how these spinners are displayed. So if you say, like, for example, get all, you'll see there's this cool animation with some spinners and things like that and colors changing. All of that is happening because of this. And so you can check out Rebel Terminal Async on crates.io, and the source code is on GitHub to get a sense of that. But now let's focus in on just the tracing config portion of that crate. So when we look at, so what happens is a tracing config gets created based on what was passed in to clap, and then that tracing config is used here using something called tracing setup, and it goes try create layers. So now we're going to jump right into layers, subscribers and layers. So let's go look inside of this thing. Okay, so now we're in a separate repo. This is actually Rebel Terminal Async, and inside of that there's a module called tracing setup. And the tracing setup module has a function called try create layers. And what this does is that depending on what information you give it in tracing config, whether you want a formatted subscriber to output a standard out to file, or to standard out and file, to standard out file and standard out and file, depending on those, it will basically create certain layers. And layers are a concept in tracing, in the tracing crate, which allow you to take a subscriber and then essentially create multiple output targets for that subscriber. So when you call info, warn, error, those macros, they emit events. And when you have the instrument derive the attribute macro, it generates spans. So spans are, they wrap functions and then log the info, log emitting via info, warn, debug, and so on. That's happening inside of a span. So that's the event source. The event sink is the subscriber. And this is a formatted subscriber. And that formatted subscriber, you can configure it by attaching any number of layers. In that simplistic example we saw, that's just a formatted subscriber that dumps everything to standard out. This is a very sophisticated subscriber, which doesn't do that. What it does, it doesn't even create a subscriber, if you noticed. It just creates a bunch of layers. And what the layers, what that looks like is, so essentially, let's look at this one. The way layers work with the subscribers is that subscribers can take a vec, which contain option of layer. And so the idea here is that you can have any number of layers. You have to erase their types because you don't want to make the distinction between a rolling file appender layer and a standard out layer, or like a custom layer that which emits to asynchronous standard out from that Rebel terminal async crate. Like it can literally be anything, or it can be something that sends log events to an OpenTelemetry collector. So we have very little information about the specifics because we don't really care. We want Rust to forget, and so this is type erasure in action. So we're actually erasing the type off the layers as we're making them. So what we do is here's an example of a level filter. So the level filter is a layer which eliminates, like for example, if your level filter is info, you won't see any trace or debug. If your level filter is debug, then you'll see debug, info, and all those other ones. You won't see trace. So what this does is that it creates a layer. Every time we do a push into this returned vec, which is a vec of basically type erased layers that are boxed. What we do is that, okay, so we jam a level filter in there. Then here we are creating another layer. So this is a layer that essentially allows, it's basically a fancy way of emitting to standard out, standard error, or that thing called shared writer, which is what's actually happening in this tcp-api-server. And this is some sort of asynchronous mechanism to display output to standard out without clobbering the prompt, which is also asynchronous. So this is what try create where'd it go? Try create display layer is, and then we have try create file layer. So this is basically, again, depending on your tracing config options, you can specify if you want to output to file or not. And if you do, then this layer gets created. And what this thing does is it creates a rolling file appender. And that's actually provided to us by the Tokio itself. And so what that does is you basically say that the rolling file appender is nice because it's not just going to make a file of infinite size. You can have policies for when it rolls over, like every hour or every day. You can set limits on how big you want and all kinds of things. It's really nice. This is a rolling file appender. You can check it out. It's really, really good. We're just leveraging this rolling file appender, but what happened was when we created this layer, we create a, like if you see the return type is concrete, but when it is, look at this, din layer, option box din layer. So basically this din layer thing is that. So so basically when we end up, actually this should be din layer. Oops. I will fix this later. Why is this? Oh, because I'm in the wrong crate. Okay, I will fix this later. I'll put a little to-do here for me. To-do, actually, I'll put this like this. AI replace with din layer. This is in a separate crate. That's why I'm actually in the TCP API crate. So this is in a different crate. It just so happens I have the source code here. Okay, so let's come back to what we're doing. So we created a vec which holds a essentially type erased layer, basically trait pointers, and then we push a level filter, then we push a display filter. So this is for, a display layer, which is for standard out, standard error, or shared writer, and then a file output layer. So the cool thing is that once we return this, if you notice, they are, let's see, let's go back to try create layers. Okay, so here, depending on what options you pass to via clap, certain layers will be created or not. And so what you get back from try create layers won't be the same every time. It depends at runtime on what configuration options you're passing it, because those options are created when you type, let's see, when you do this. See, when you say, actually, let's just do dash help. We don't need to, oops. So let's see here, when you see, let me clear the screen. There we go. So here you can see -t, and these are the arguments you can pass -t. So depending on what you pass it, you will get some layers or you won't get other layers. And so this comes back with a vec. We don't know how many we're going to get because it depends on what we typed here. So you say target, you can say server dash dash, let's see, -t, and you can say like standard out and file. And so now when we go to try create layers, we're going to get a level filter, we're going to get a display filter, and we're going to get a file filter. Or a file layer, sorry, display, what am I saying? We're going to get a level layer, level filter layer, actually. Then we're going to get a display layer and a file layer, which is cool. And so we'll get 3 layers in this case. And then we're not done yet. That's just the layers. We haven't put them in a subscriber yet. So if we look at the try create layers, there's an init function that's above it. And you can just call init. It's just quicker because maybe you don't want to do anything more complicated. You just want to say, like, this is complicated enough. So you just say init, giving the tracing config, and what it does is it create a bunch of layers. And if you have any layers, meaning like you didn't say none, because when you say none, this vec is empty. Actually, it's not empty. It'll just get none because it's optional. And so when you get the layers back from here, assuming you have a vec, then it will take those layers and it will give it to the tracing subscriber registry function with layers. And then this will basically add these layers to this subscriber and initialize it. So that basically gets it done in one go. Or you can do it in a more complicated manner like what we're doing, because we want to compose other layers. This is just the beginning of the journey. So here we have the create layers, which just creates those standard out, standard error, shared writer, and file layers. And then what we're doing here is that if this is some, that means you didn't say none. Then it will grab the Jaeger setup, and it will module, and it will create an OpenTelemetry layer. which is kind of complicated. So let me talk about what OpenTelemetry is in a moment, and I'll show you what all of this running with Jaeger, so we can see the output. So OpenTelemetry is, so the tracing stuff is Tokio specific, but it maps really nicely to OpenTelemetry. So what the heck is OpenTelemetry? Let's look at this. Oops. So this actually is a really nice tutorial. It's out of date, unfortunately, in the Tokio RS, the main Tokio documentation site, under next steps of tracing. And it'll walk you through, configuring an example so that you can integrate it with OpenTelemetry. And it'll say, hey, you can run from Docker, you can get this thing called Jaeger, and then you can, it's a collector, and it's a web application that allows you to analyze and visualize your spans. And all of this is unfortunately out of date. Here is the correct, or it's all deprecated, by the way. This is deprecated. Which one is deprecated? I think this one is gone. Yeah, this one is deprecated. So here is the oh, I'm in the wrong crate. Let me bring another. Oh, let me show you this. In order to see this, we have to go to a different crate. Let's do this rebel. So in order to see the correct, here's the correct one. So yeah, so OpenTelemetry. So we still need OpenTelemetry, but the version is now 0.22.0. We still need tracing OpenTelemetry. This is to connect OpenTelemetry to tracing crate, and I'll explain why that's necessary in just a moment. We don't need OpenTelemetry Jaeger anymore, and instead we replace that with OpenTelemetry OTLP. This is the protocol that's used for OpenTelemetry to send messages from exporters to collectors. And yeah, that's essentially it. So this is the correct new imports. But beyond the imports, we have, let's see, a different way to even create these. So here it just says to do this thing called globals. This is gone. This is gone. And that is still there. And yeah, so basically it's, this is the old way, and this has all been deprecated. The new way is, let me walk you through this. Okay, so last we had looked at this, our journey, we were trying to get, yeah, we had created a bunch of layers for tracing, for file, standard out, standard error, shared writer. And we wanted to augment that. We wanted to extend that layer. We wanted to add another layer for OpenTelemetry. And so Jaeger setup has is a module in Rebel Terminal Async, and in that module there's a function called try get OpenTelemetry layer. And what that does is that, similar to when we created a layer for standard out, standard error, file, and all that, this one does a similar thing, but now it's for OpenTelemetry. And so OpenTelemetry is an open standard, as the name would imply, and it essentially maps the Tokio concepts, and then it makes it an open standard, so it's not Tokio specific. So this notion of span is still valid. Spans have attributes. They're distributed, and you can have a beginning and an end time for a span. You can have a whole bunch of spans nested within them. And a trace is made up of one or more spans. So yeah, so basically that's what our Tokio stuff maps to in OpenTelemetry parlance. And all this is handled under the covers. You can read more about observability with OpenTelemetry here and what their definitions of these things are, but roughly they map pretty consistently to the Tokio tracing stuff. And so this is an example of the new way of doing things, which is different than what is shown here, because this is out of date, unfortunately. And then Jaeger is this OpenTelemetry collector, and so basically, what we're doing in this OpenTelemetry layer is that we're creating a emitter that will essentially the subscriber for tracing. We had a formatting subscriber. This is an emitting subscriber. So this will take all the events that have come in because of all the log events that we've generated, which are wrapped in spans. All that is going to be sent to the subscriber, and the subscriber will pass it to this layer. And what this layer does is that it will collect those log events and send them to an OpenTelemetry collector. And that OpenTelemetry collector is a separate process that's also going to be running on this machine. And then we'll be able to visualize that OpenTelemetry collector we're using is called Jaeger. It's made by Uber. It's open source. It's kind of nice. And we'll be able to see a visualization of what all of this thing looks like. So it's not only a collector, but it's also a nice web application that that we'll see in a minute. And the way the collector works is you can use a variety of different ways. Like there's, we're actually going to be using the gRPC. We're going to be using OpenTelemetry protocol over gRPC. That's how we've configured this. So with kind of like a whirlwind, by the way, this is a really good blog post. I'll put a link to it. It covers some of the stuff. So let us look at this real quick. So let's see, let's put this here. So when we go to create an OpenTelemetry layer, so this is the thing that will take, it's going to be put in the subscriber. The subscriber will receive the emitted log events, and then it'll send it to a collector, which is Jaeger, and then that's the end of that journey, as from this thing's perspective. And so what we do is all these types aside, the first thing that we do is we check to see is the Jaeger up and running. And the way we do that is because we know when we configured Jaeger that we're going to be using gRPC, and I'll show you where that's set up in a minute. We check to see, hey, is port 4317 available, or is something bound to it? Is it used up? Is it unavailable? If it's unavailable, that means Jaeger is running. If it's not, then it isn't. And so if Jaeger is up, then what it does is that this is where the actual work happens. And I have put a lot of comments in here. Definitely check out the source code as you're watching this video or after you watch the video. Let me walk you really quickly through what's happening here. So here we're creating a new OpenTelemetry pipeline. And what we do is that we say, okay, we're going to be using gRPC. And this is the port, the host and the port where the collector is running. So we're going to be exporting using gRPC to this collector, and that collector is Jaeger, and that Jaeger thingy is running on 127.0.0.1 That's where that's configured. So if you have a different collector, you need to change this this URL. And if you don't want to use gRPC, then don't use Tonic. There's other HTTP, HTTPS, and a whole bunch of other things you can use. And what this is saying is that this is part of OpenTelemetry again, like it's part of the standard where you have to and you'll see this in the UI where depending on when we see the traces, we're going to actually see two top level buckets. One is going to be server and one is going to be client, and that's how this is connected. And then finally, we have this thing called install batch, and what this does is that this pipeline, when an event comes in, it won't send it to the collector right away. It'll batch a bunch of them and then send them periodically, and that's for performance reasons. So you can read what's going on here. It is an asynchronous batch thing that's run through Tokio. Okay, so that's try and exporter. So once, if we can get a tracer, that's called a tracer, with all those configurations, then we can turn it into a layer. And then what we do here is that we have something called drop tracer, and I'll explain the use of this in a moment. But because we were running this tracer, this emitter, which exporter, basically, it's attached to the subscriber, takes the event, sends it to Jaeger. This thing needs to be shut down when our program is finished, so that it can flush its cache or its queue or whatever, because it's batch uploading those events. So there's this thing called shutdown tracer provider, and that needs to be run when your program ends. And what I did was I just implemented the drop trait, and I'll show you how I use it in a minute. So that's what try get OTel layer does. So this comes back as a layer, just like those other layers. This one, the file, rolling file appender, and standard out, standard error, and shared writer, and so on. We just take the vec we got from try create layers. We just push this OTel layer into it. And we track this, we basically create a variable called maybe drop trace, and we're not going to use it, but what happens is this variable will be dropped when main function exits, and what happens is when it gets dropped, it will do this. This one. It'll call global shutdown tracer provider. So that will ensure that we don't lose any traces. That's essentially what's happening here. And then finally, the layers, all of the layers, are then added to the tracing subscriber registry, this registry object, which is initialized. And that is how this whole mechanism or machinery is put together, and it's up and running. This is something else for me. I'll do a whole video on me later after I do the async one. So all of this is these few lines, actually mostly these two, is how the layers get created. This is how the layers actually then get put into the tracing subscriber, and that gets installed so that all of this can work, and I'll show you this working in a minute. And then finally we have this drop thing, this one, drop tracer. And this will get dropped when the main function exits, and that will shut down the OpenTelemetry exporter. So with all that said, let us see if we can visualize this, because that was a lot of code. I haven't actually shown you what this looks like. So let's see. Let's see what's going on with Docker. Okay, so nothing is running, so that's great. So we can do Docker up. Actually, let's look at I have this in the README actually. By the way, you can read through all the README for architecture on the whole tcp-api-server. I'll do a separate video on that, and I'll also do a blog post on Developer Life about it later. So here, you can just say docker compose up, and if I don't do -daemon, then we'll see the Jaeger running here. So there's Jaeger. And then Jaeger's running on whatever this is. So we can now look at it there. Check that out. There's Jaeger. There's nothing in it because, we haven't done anything. So let's run the server. Let's run the client. So we'll say size, get all, quit. Oh, what the? OpenTelemetry trace error occurred. What? Okay, let me do this. Docker, let's see, Docker PS, is it? Nope, Docker compose up -d. Okay, is it running? Okay, it's running. And then let's redo this, search. Okay, nothing, no traces to find, that's good. Okay, let's run the server. Actually, let me quit this real quick, clear the screen so we don't have so much garbage. Okay. So we say size, so get all. These are just different functions, and they should be populating. Let's see. There we go. So I'll walk you through this in a minute. So I don't know what I did wrong with the Docker Compose up in the other window. So then let's just kill the server for now. So I've killed the server and the client. That basically emitted a bunch of log events to stdout and to file because that was going the whole time. Additionally, though, it uploaded all of these events into Jaeger. And this is just running on localhost, so we can visualize it. Check it out. So there's Jaeger all-in-one is actually events generated by this itself. So we're not going to look at that. We're going to look at client. So when you look at client, you'll see these are the main functions that are actually being executed. So you can see, let's see, client main. This is the network IO thread, and this is the thread that takes commands from the terminal. So if we look here, you'll see that, let's see, it has monitor user input event. Check it out, the client ID. So this client ID is that Bell grapefruit thing. And this essentially, you can even search for this. You can just search for Bella grapefruit. And see how it's highlighted in yellow, all the places where it found Bella grapefruit. So basically what this is saying is that there's a thing called client main, monitor user input event loop, which is in this one. So you can actually see monitor event loop, monitor user input, this thing. This thing is the thing that a function that generated the span. And it has the thing inside of it. It goes Bella grapefruit 844. So this is that. So cool. And this actually client ID was received from the server. So even though it came in from the server, it got recorded here. Span current record, and then this thing client field ID. This is basically where we get this value from the server and we set it, and then tracing will pick it up and then populate our logs subsequently. This is absolutely magical. So now we know that Bella grapefruit 844, this client, is responsible for all these messages. That is so cool. So we can see what they did. They sent a client message because it's send a client message. So when I typed size, this is what got logged. Then I typed get all, and that's that. This is the representation graphically of the session. So then that's a thread that did the user input event handling. There was another thread that did the network handling, the TCP connection with the server. Let's go look at its journey. Check that out, Bella grapefruit 844. So it's the same session, even though it's a separate thread. This is so cool. And then here we can see the messages that came in from the server for Bella grapefruit 844. So the first one that came in was send client ID, which is awesome. This is the thing that actually set this ID. So this is just magical that at the start of this function, we didn't know this ID. As the protocol kind of did its thing, we got the ID, we set it in the record, and then now it showed up in the tracing. This is amazing. And then here we see, which one is this? The size. This is a response saying, I typed size, it went to the server said, okay, the size is 3. And this is get all, the response for get all. And you can actually see the string. Look at this, the debug output for that struct. This is all happening thanks to instrumentation. And this is on the client side of the journey. So if we look at the server side of the journey, we'll see a completely different sequence of events that go down, which is amazing. So here, so the server, and this might be a really good way to understand the code in tcp-api-server, is just, look at it in runtime and kind of see what it's doing and then map it back to the source code, or maybe go the other way around, or maybe bidirectionally. So the server process, once it spawns up, it it creates a handler for each incoming client connection, which is why almost all the work is happening there. There's other things it does, which isn't this is more maintenance things, like it sets up a control C handler. It loads the key value store from disk, which is really cool. You can kind of see the life cycle of the server itself. This is just, it's in a loop waiting for connections to happen. And let's see. Oh, actually, we saw this already. And then let's do this one. I think we started the server more than once. That's why there's two of these. So here we can see this is the actual sort of what is going on. So Bella Grapefruit. So this is a session for Bella Grapefruit that is being handled in this thread. So that's why we get its own like trace or span. So, and inside of this we have for Bella Grapefruit all the things that are happening with Bella Grapefruit. So the first thing is we got a size request. Then we created it accessed the database or the key value store. It got something from the key value store, and you know, that's the kind of life cycle that happened. And then this is the handle client task. There's another one. Let's see for oops. Let's see, handle client task. We have, let's see, this one, get all, so size get all, and I think this one is exit. Very cool. And then let's see, those are most of the spans it looks like. Then we have let's see, this stuff, and then this one is, let's see, Lucy Strawberry. Oh, this is a different session actually. Oh, that's why there's two sets of these. So there is, so basically these are all the things that we instrumented in the server. We actually instrumented more on the server, actually more on the client than the server, because the server also sends messages to the client, but I don't think I instrumented those. But that's why they're not showing up here. But on the client side, it shows both the receiving and sending side. So with this, we are actually at time, and I've pretty much covered everything I wanted to cover in this video. I'll put a link to, I'll share all these links in the description of the video. So if you like this style of video, please give it a thumbs up. Please subscribe to the channel because you'll be notified when the next video is published. And also check out Developer Life, which is, this is the YouTube channel for all of this. And I'll create a blog post here for this, and please subscribe there too so you can get the content updates. And yeah, in the next video, or next videos, I plan to cover async in detail and like complicated stuff with how do you create event loops from scratch that are fully asynchronous and non-blocking, how do you handle shutdown, really low-level stuff like that. And then I'm planning on doing another one on Miet and a few more. So stay tuned. There's more content coming. Thank you so much for watching. Oh, and actually, I'll share a link to this. All the code that I've shared is in this repo. So I'll put a link to this in the description as well. Thank you so much for watching, and hope to see you in the next one. Take care.